That's disturbing. There shouldn't be anything else. Still just me here. Just posted. Okay, well, let's get the camera fired up. And you're like the worst. I don't understand. Why don't you have a window? There it is. Okay. Good morning, guys. All right, as folks are starting to arrive, we will go ahead and get started. There are a few kind of review type things that I wanted to talk about before we jump into the material in earnest. So the first official topic for this week, the first thing that you have, for example, homework problems on, is section 2.2 in the textbook. But before we jump into that, I just wanted to talk a little bit about, like we said, the shapes of subsets of real numbers. So I want to talk about intervals, open intervals, closed intervals, what's called the topology of the real numbers. Because there's some stuff that's a little bit weird that you don't usually discuss a whole lot in a pre-calculus or college algebra class that is, in our setting here, very, very important. It turns out the idea of an open set is a lot more general than you may think. And open sets are kind of the whole thing for doing calculus. If you want to do calculus in higher dimensions, if you want to do calculus in other spaces, it's all about being able to define what an open set is in that space. In the real numbers, most of the open sets that we care about are open intervals. So I want to talk just a little bit about open intervals. I'm going to switch over here to the dot cam. It looks like Zoom updated, so make sure I've still got everything as it was, still recording. Oh. Okay, so before we begin on chapter 2, this is my good pen here. I want to talk about open sets. So. The big challenge with discovering calculus, thank you, yeah, so towards the end of class, I am going to take roll. I'll just have everybody type the word here in the chat, but I don't want to do it now. I want to wait until a few more people have shown up, but thank you, Andrew. So the big challenge with inventing or discovering calculus, whichever you believe Newton or Leibniz did invent or discover it, was with coming up with the formal concept of a limit. And that's what we're going to talk about mostly in chapter 2, is this idea of a limit of a function. And you may have seen a little bit of that in pre-calculus, you may not have. Either way is okay. But it turns out that the underlying thing over the hundreds of years that have passed since then, when we want to kind of deepen our understanding of what calculus is and how it works, turns out to be this concept of an open set. An example of an open set, and when I want to discuss an example, I'll always use this abbreviation, this Latin abbreviation, e.g., for example, Scrati, or for example, open intervals. The study of open sets in general is called topology. And you may have heard people use that word before in a math class. There's a much more, there's a larger world than we're going to talk about of topology. It's a huge field of mathematics. But for us, we're really only interested in the open sets in the real numbers. So open intervals are open sets in R. And this is the symbol I'm going to use when I want to real numbers all together. So the interval from A to B. This will also let me just introduce some notation. So this curly brace means the set containing, and this is x, right, just the variable x. So this is the set containing all of the variables x in the real numbers, such that A is less than x is less than B, right? So this is called set builder notation. You may have seen this in your pre-calculus class. Some people use a colon here instead of a vertical line. That vertical line is called a pipe. Either way, that's read as such that. So this is the set of all x's that are in the real numbers such that A is less than x and x is less than B. So it's the set of all real numbers strictly between A and B, right? And if we want to draw this, I might put A over here and I might put B over here. The reason the concept of an open set is so important in calculus and so important for purposes of limits is because there is no largest number in this set. There's also no smallest number in this set. So open sets are the right place to start talking about the concept of a limit, because you have this idea of getting closer and closer and closer and closer to something, but not quite being able to get there. So an observation there is no largest number in the open interval AB. If you think you have some possible largest number in this set, observe the following. In order to be in this set, it has to satisfy this restriction, meaning it has to be strictly less than B and strictly larger than A. So if you take some guy in here, X, and you think, oh, well, maybe this is the largest number in that set, you can zoom in here and there's always going to be some space between that X and B. Why? Because X is strictly less than B. If there wasn't space between X and B, that would mean X is equal to B, but then X couldn't be an element of this set. So, okay, well, maybe you think I can look a little bit to the right there and find a candidate for the largest element of the set. But then you have the same problem with that. You can just zoom in and this gap will always be here. Similarly, there is no smallest number in this set. Right, so an open interval contains neither a largest element nor a smallest element. The only reasonable candidate for the largest element of the set would be the number B itself. But B isn't in the set because it's an open set, right? This is an open interval, and remember, open intervals don't contain their endpoints. So this interval has all the numbers that are like a little bit smaller than B, but not B itself, and all the numbers that are a little bit bigger than A, but not A itself, which means that within this interval, you can kind of sneak up on B. You can get as close as you want to B. There are lots and lots of numbers in here. If you want a more concrete example, the interval, let's say 0, 2, has no largest or smallest number, right? And if you want to look for a largest number that's in the interval 0, 2, the open interval 0, 2, the only reasonable candidate would be 2 itself, right? But 2 isn't in there. And then you might ask, well, okay, well, what's the next smallest number, right? If I try to step back from 2 a little bit, is there a real number that is the next smallest? And the concept of an open set is linked to the concept of a limit, because the answer to that question is no. I mean, sure, okay, 1 is in here, but there's infinitely many numbers between 1 and 2. And so if you want to try and think, oh, well, what's the next biggest number? Then, oh, you could say maybe 3/2 or 1.5. But then there's infinitely many numbers between 3/2 and 2. And you can keep doing this, right? You can keep chopping this up. If you wanted to look at the next guy, you'd have like 1 3/4. That'd be 7/4. And you can keep playing this game, and you can get as close as you want to 2 and stay in this interval. But you can't get to 2 and stay in this interval. There is no largest number in this interval. And similarly over here, you could play the same sort of game. You could say, okay, well, what if 0 isn't in the set, but I want to come up with something that is the smallest element in the set? I should see what can happen if I walk in from 0 a little bit, maybe here to 1/2. But then, of course, there's also 1/4. And then in here would be like 1/8, and then 1/16, and then 1/32. So there's neither a largest nor a smallest element in that set. You can stay in the interval 0, 2, and come up with numbers that are very, very close to the largest element in that set if you want. You could think like 1.9, 1.99, 1.999, 1.9999, but you'll never actually find a largest number in the set. The idea that this leads to is called the supremum and infimum, or the greatest lower bound or least upper bound. And if we were in just a slightly more advanced class, if this was a real analysis class, that's where our discussion of calculus would begin, is with this idea of a supremum and an infimum. But since this class is more about skill building, this stuff is mostly just for your enrichment. It's not necessary for the skill stuff. But I do want you thinking about these sort of things as we go through the class. So it turns out that open sets are very important for calculus because they introduce this idea of getting very, very close to something without actually getting there. So if I want to stay within the set 0 to 2, the open interval 0 to 2, I can't get to 2, but I can get very, very close to 2. I can't get to 0. 0 is not in the set, but I can get very, very close to 0. And that is kind of the fundamental principle that underlies this concept called a limit. So that's what we're going to begin talking about now. Before I start in on chapter 2, did anybody run into any trouble getting registered for WebAssign? Does anybody have any questions about the sort of syllabusy stuff that we went over in class yesterday? Any questions about the course structure or online components, things like that?
No, sir.
I'm sorry, Sergio, if you said something that I couldn't quite hear you. Can you repeat that?
No, I said no, but thank you.
Oh, okay, cool. All right. So let's start on chapter 2. So chapter 2 has a section in it that we're not going to cover. Section 2.1 kind of starts by talking about tangent lines and slopes. We're going to build to that discussion. I think that the book is a little bit out of order in a sense there. So the first thing we need to talk about in order to even approach the concept of a tangent is a limit. And the idea of a limit is really just this. I'll give you the definition. So we say the limit as x approaches some number, and I'll call that number a, of the function f of x is equal to L, provided, and again, this is very intuitive, as x gets closer and closer to A, the outputs f of x get closer and closer to L. So this is the kind of intuitive definition of a limit, and it's important that you internalize this fully. Let me draw a picture. So here I'm going to have the graph of some function f of x. Here I'll mark this as a, and then maybe f of x looks something like this. So if I take x's, which are very, very close to a, maybe I have x right here, is it true that the output, f of x, is very, very close to L? Well, there's x and f of x, and here is a and L. Big points. So imagine I move this x closer and closer and closer to this number a. If I let this guy get closer and closer and closer to this guy, will it be true that this y value gets closer and closer and closer to this y value? It's not too hard to imagine. Let this point start walking to the left. So I just start moving this x value closer and closer to this x value. Then the point on the graph up here is going to walk along the graph and get closer and closer and closer to this point, right? And the y value at this point is L. So in this picture, I would say the limit as x approaches a is L, because this point does get closer and closer and closer to this point as I move along the graph with this x approaching this a. So this is the kind of intuitive picture. And you might ask, well, why have all this special language and why have all this definition at all? It seems like every curve should do this. There's nothing special about this picture. If you took any graph, any function, wouldn't this happen? If I take 2 points that are on the graph and I keep one of them fixed and I let the other one approach the first one, doesn't that mean that the y values will get closer and closer together? And the answer there is yes, if the curve is continuous. So because I've drawn this picture to be a graph of a continuous function, and we're pretty much used to just looking at those from our pre-calculus class, the answer there is yes. But continuity turns out to be a subtle goddamn thing. And so this idea, we want to see what we can do if I stop drawing this picture as a continuous curve. I want to see how I can break this. I want to try and understand, when does this happen and when does this not happen? And it turns out that the interesting part, at least for now, for us, is going to be answering the question, when does this not happen? So I want to draw a few more weird pictures and try to open your eyes to this idea that, that maybe this doesn't always happen. And then try to see what kind of broken pictures still allow this to happen. So first, before I do that though, the notation. If the definition above is satisfied, we write lim x to a of f of x equals L. Sorry, here we go. So this is the notation. Now there's actually something a little bit subtle. We're going to talk about a technical definition for the limit in a minute, but this is the regular notation. So this says the limit as x approaches a of f of x is equal to L. And that's because if I take an x that is close to a here, and I send it closer and closer and closer and closer to a, then the outputs, f of x, will get closer and closer and closer and closer to L. If I approach from the right like this, then the f of x's will be smaller than L and getting closer and closer. In this picture, if I were to approach from the left over here, then I would be getting closer and closer from above. And it turns out that the kind of subtle thing is what's called a one-sided limit. So when you approach from the left, does the same thing happen as when you approach from the right? But this is the intuition. This is the basic idea behind a limit. So before I get into the sort of technical definition, are there any questions about the sort of intuitive definition? Do you feel like you understand what's being said here? Is there anything you'd like to ask or talk about? Sometimes these concepts can be investigated numerically using calculators or computer algebra systems, and limits are a good example of something like that. So if you feel like you're not quite grasping the intuition all the way yet, don't worry, we will do some computational examples. So can this ever fail to happen? And when I mean that, having a limit. So my first example here would be if you take something that's like a piecewise function. So maybe I have, I don't know, some linear function. Let's draw it like this. So this could be the graph of a piecewise linear function. This might be something like f of x equals negative x plus 3 if x is less than and it might be, let's say, x minus 2 if it's not going to work, x minus 1/2, let's say, if x is bigger than. So just coming up with a formula that might work like this, right? So here's the number 1, this up here would be 3, and then this guy right here, 1 would be 1/2, and this guy right here, 2. Okay. So here's the graph of a function. It's definitely a function that we could play with, right? We all learned about piecewise functions in pre-calculus. So this is a function defined piecewise and its graph, and each of the pieces is linear, so it's not a terribly hard to understand function. But I'd like to ask, what can we say about the limit as x goes to 1 of f of x? So I want to take that idea that we just discussed on the previous page and see if I can't apply it to this function where a is equal to 1. And remember what that definition said. Say that the limit of a function, the limit as x approaches a of the function f of x is equal to L, provided as x gets closer and closer to a, the outputs f of x get closer and closer to L. So here I'm asking what happens as I let my inputs, my x's, get closer and closer to 1. Well, if I take an x over here, that's to the right of 1, and I let x get closer and closer and closer to 1 from the right, like this, then what are the outputs getting closer and closer to?
Does it get closer to infinity?
Mm,
No.
not infinity. So let's look at the picture. If I let this x value get closer and closer to 1,
Oh, one.
the point along this graph is getting closer and closer and closer to this point, right?
Yeah.
So those outputs are getting closer and closer to half. Does that make sense? Yeah, good. So as x gets closer and closer to 1 from the right, the outputs f of x are getting closer and closer to 1/2. So this is an important observation about this function. And what about moving in from the left? As x gets closer and closer to 1 from the left, the outputs f of x, what are they approaching?
They approach 2.
Good. So with these two observations, I'd like to ask the question, is the definition satisfied? Could I say that this function has a limit at 1? As x gets closer and closer to 1, do the outputs f of x all get closer and closer to some fixed number? It's kind of a subtle question, right? So when a mathematician looks at a definition like this, they say, okay, I need to be able to specify a particular number a, and I need to be able to specify a particular number L. And then with those two particular numbers in mind, I read the definition and I ask, is this sentence a true statement? Suppose here a is 1, right? We don't have any control over that. We're looking and seeing what happens when x gets closer and closer to 1. So let's read this definition with a as 1 and L as either of these two numbers, 2 or 1/2. The limit as x approaches 1 of the function f of x is equal to 1/2, provided as x gets closer and closer to 1, the outputs f of x get closer and closer to 1/2. Is that a true statement for this function? Only if we approach from the right. If we approach from the left, that's not a true statement, because then the outputs are getting closer and closer to 2. If we try to reread this sentence with L equals 2, then it's only true as we approach from the left. It's not true as we approach from the right. So this is one example of how a function can fail to have a limit. And there is some specific notation for all of this. This statement right here, I can describe as saying the limit as x approaches 1 from the right, and we write a little plus there, meaning the x's I'm considering are a tiny little bit bigger than 1, of f of x is equal to 1/2. And the second statement, I can write that as saying the limit as x approaches 1 from the left. And when I say from the left, I use a little minus there of f of x. This is equal to 2. So each of those sentences that we wrote down where we're considering sneaking up on 1 from the left and sneaking up on 1 from the right have their own notation in this limit language. And it turns out, and for us, this is the definition of a function having a limit. This is the definition that the book gives, the formal definition, we say the limit as x approaches 1 of f of x exists if the left and right limits are both equal to each other. So here the right limit is 1/2 and the left limit is 2. So overall, I would say that the limit as x approaches 1 for this function does not exist. Do you feel like we understand what's going on with this example? Are there any questions about what I just said there with the left and right limits not being equal?
No, sir.
All right, so the answer,
Can you just visually show me how it approaches 2?
yeah, sure.
Thank you.
So the answer to the question we asked earlier, what can we say about that limit? If we want to go back and be thorough and fill it in, that limit doesn't exist because the left and right limits aren't equal. Okay, yeah, let's come back to this. So if I want to start looking at outputs that are, if I want to start looking at inputs that are very, very close to 1, but on the left, and then seeing what the outputs are like, that means I'm going to imagine that my x is over here, right? So the point associated on the graph with that is going to be up here. And as I bring this x closer and closer and closer to 1, this point is going to get closer and closer and closer to this hole, right? And the y value at that hole is 2. So this might be a good example of a place where we can investigate a little bit with a table. If I wanted to, I could actually make a table of x and y values for this function. Let's do that.
Okay, cool. So we don't have to use the same x value. It's any x value, essentially, that is going to approach the hole.
Yeah, if I wanted to investigate this limit numerically, what I would plug in x equals 0.9, 0.99, 0.999, 0.99999. I would start plugging in x values that are closer and closer and closer to, but not equal to 1.
Cool.
And as I do that, if the x values I plug in are a little bit smaller, like 0.9, 0.99, 0.999, and so on, then I'll see that the y values are going to get closer and closer and closer to 2. If I plugged in x values that are a little bit bigger, like 1.1, 1.01, 1.001, 1.0001, and so on, I would see those y values getting closer and closer to 1/2.
Hence the piecewise function.
Yep.
Of what says if. Okay.
Yeah,
Thank you.
it's this here that's doing that for sure. Does anybody else have any other questions or thoughts they'd like to add? So I always imagine a little dude walking along the graph, right? I imagine zooming in here and having a little guy that walks along the graph. And he's going to walk along that graph towards the place I'm interested in from the right. And he's going to walk along that graph towards the place I'm interested in from the left. I think once to my Calc 1 class, I described this as like a dude and his girlfriend, right? They're trying to meet up. And one coming from the left, one's coming from the right, and we ask, do they actually meet up? Do they get to the same place? If yes, then the limit exists. If no, then the limit doesn't exist because the left and right limits must be different. Here, if this is the dude and this is his girlfriend, then as the dude gets closer and closer to x equals 1, he's going to end up here at 2. And his girlfriend, trying to do the same thing, just coming from the other side, she's going to end up down here at 1/2. So they're not going to be able to meet up. So we would say that this function doesn't have a limit at 1. And observe that, of course, the function is discontinuous, right? This is not a graph of a continuous function. So
I have a question, Mr. File Sticker.
What's up?
So between the two open dots, if there was a solid dot right in between those two, what would that be considered? Yeah.
So that actually doesn't have any effect on the limit because everything that we wrote here is still true. You can imagine that, right? If I happen to change the definition of the function just a little bit to include the fact that it's exactly equal to 1, if x is exactly equal to 1, then everything we just said about the limit is still true, right? As we approach from the left, we're getting closer and closer to 2. As we approach from the right, we're getting closer and closer to 1/2. So we could do that, and it won't change anything that we said about the limit. And what you're getting at here is the basic idea behind continuity. So it's jumping the gun just a little bit, but it turns out that a function is continuous if two things are true. Continuous at a point, say a, if the limit as x approaches a exists, meaning the left and right limits are both the same, and also the value of the function is equal to the limit there. That's something we're going to talk about when we get to section 2.5, so don't stress about it if it's not clicking right away. For now, we're just worried about getting this idea of a limit internalized. So the big thing I want you to take away from this example is that the left limit and the right limit were different. And that means that the limit overall doesn't exist. The notation for the left limit is the same as the notation for the regular limit, just with a little minus above and to the right of the number a. And the notation for the right limit is the same as that, but with a little plus. Okay? So I'd like to look at a few more examples like this. And in your first homework, most of the limit examples that I ask you to work, at least at the start from 2.2, they're all coming from pictures. They're all coming from pictures of graphs like these. So imagine I have something like this. It's like a parabola, except it's got a hole. This could be coming from a rational function where there's a factor at the top and the bottom that cancel. You may have seen that in your pre-calc classes. Maybe this hole is over here at 2. This up here could also be 2. Well, let's say that that's 3 just for fun. Okay. I want to do the same thing. So this is the graph y equals f of x. It's my x-axis. And I want to know the same thing. What can I say? About the limit as x approaches 2 of f of x. Well, the function isn't defined at 2. But if I imagine walking along the graph from the left, that is, I imagine my little dude over here, and he's walking that way. He's approaching 2 from the left. Where is his y value getting closer and closer and closer to?
3.
Yeah, right. He's getting closer and closer and closer to this y value, which is 3. So I would say that the limit as x approaches 2 from the left is 3. What about the limit as x approaches 2 from the right? Oh, I wrote 2, didn't I? Sorry, this is 3, yeah. So what if the dude's girlfriend is over here? Sorry, these are my really bad stick figure drawings. It's 2020, we don't need gender. So the dude's partner is over here and trying to meet up at this x value of 2. As you walk in from the right, what are the y values getting closer and closer and closer to?
3.
Also 3, right? So what could we conclude? What can we say about the limit as x approaches 2 of f of x? First, does it exist?
Yes.
It does, right? The limit lim x approaches 2 of f of x 1 does exist. And what else can we conclude? and is equal to 3. i.e. lim x to 2 of f of x equals 3. Right. So this is the notation. This is how we would write this. And we'd say that because these two are equal. Is this function continuous?
No.
It can go to infinity.
But what about the whole? No? I don't know.
Good, yeah. Things we want to be asking. So there is a whole. And remember, in order to be continuous at a point, you certainly have to be defined there. So here, f of 2 doesn't exist. But even though f of 2 doesn't exist, the limit as x approaches 2 of f of x does exist. So here, f definitely is not continuous at x equals 2, but it does still have a limit there. And that's a big idea. And if you think about it, that big idea is connected to the idea of an open interval that we were talking about at the start of class. The domain of this function is a half open interval. It's open at 2 on this side and open at 2 on this side. And that's what allows us to do this kind of approach but not quite get there thing. So another thing I'd just like to observe, this is the main point, but also so f of x is not continuous. Specifically, f of 2 does not exist. I would love to say that f of 2 is 3, but there's a hole on the graph there. So f of 2 doesn't exist. 2 isn't in the domain of this function. So this function is definitely not continuous. However, it still has a limit. So even if your function isn't defined at a point, it may still have a limit there. And this is going to be the critical idea when it comes to defining the derivative and talking about tangent lines. We're going to end up playing with an expression that isn't defined for a particular value of a variable. But when we take a limit, we will be able to say what that limit is nonetheless. There are a lot of cool functions like this. One of the easiest ways to generate a function like the one whose graph I drew for you here is to take a rational function and then have some common factor cancel top to bottom. So let's look at just one more example, and let's start this time, instead of with the picture, let's start with the algebraic expression. So let's do, So let's examine the behavior of this function, x squared minus 1 over x minus 1 near x equals 1. Now, what I mean by that is I'd like to compute the limit as x goes to 1 from the left of f of x, the limit as x goes to 1 from the right of f of x, and draw a graph. Okay, So this is where I will go ahead and invoke the use of a table to let us do these things without working with a picture. And then we're going to see how to approach the problem from a purely algebraic standpoint. And then we're going to draw a picture and we'll do the thing that we did in this previous two examples to reinforce that. In order to do this, I think I'm going to make use of some tech. So if you'll bear with me for a second, I have a emulator for a graphing calculator. Now the calculator rule in this class is that on exams, you're not going to use calculators at all. I invite you, as you work through the homework and as you do everything else, to play around with whatever software and stuff you like. Some people really like Wolfram Alpha. Some people love Desmos. I'm a big fan of Desmos. I strongly encourage you to play with Desmos. But I think pretty much everybody has some experience with these old TI-83s. So that's what I'm going to use here. Let me do a new screen share. We'll just do the whole thing. There it is. All right, so this is my virtual TI-83. Can everybody see this okay?
Mm-hmm.
Okay, I'm going to pull him up on top of this. I'm going to come in here and whoops. Oh no, I've got my mouse has been messing up. There we go. Okay. So I'm going to type this function in. It is x squared minus 1 all divided by x minus 1. And this is a rational function. It's the sort of thing that you learned how to graph a little bit in college algebra and definitely a hearty amount of in pre-calculus. We could hit the graph button and it'll draw a graph for us. There's the graph, that's nice. But what I really want to do is play around with this table setting. So you see here, if I put in 1, I get an error because x equals 1 makes the denominator of this function equal to 0, right? So this function is definitely not defined when x is equal to 1. That's why we're saying we want to examine the behavior near x equals 1. One way to do this, I can hit second and then window to pull up my table settings. And I can have my table start at 1 and set delta table to something like 0.001. So we're going to take very small steps away from 1. And then I can bring the table back up. So what you see here is a list of values, right? On the left are x values, on the right are y values. Let me come way down here. All right. If I'm at 1.02 and I start walking closer and closer and closer to 1, what do you notice about these y values?
Slightly larger or smaller.
Yeah, well, they're getting closer and closer to 2, right? So as the x values get closer and closer to 1, the y values get closer and closer to 2. Here at 1.001, the y value is 2.001, very, very close to 2. But then when I actually get to 1, I get an error. And if we approach from the other direction, here are some x values that are close to 1 but are a little bit smaller. And as I go down the list, they're getting closer and closer to 1. As I go down this list, what do you notice about those y values? 1.99, 1.991, 1.992, 1.993. They're getting closer and closer to 2 also. So numerically, here, let's do this precisely. Let's look at f of from the left, I'm going to look at f of, what's close to 1? 0.9. F of 0.99. F of 0.999. F of 0.9, I can compute. So I'll do it the normal way here. Let me quit this. That would be 0.9 squared minus 1. I get this. And then I'm going to divide that by 0.9 minus 1. I get 1.9. So f of 0.9 is 1.9. Everybody see what I'm doing down here? So I'm just making a smaller table. If I want to know what is f of 0.99, I'm going to plug 0.99 in for x. So I'll take 0.99 and I'll square it. Then subtract 1, that's my numerator. Divide this by 0.99 minus 1. Oh, but I need to put that in parentheses otherwise. Yeah. Here I get 1.99. And if I were to calculate f of 0.999 the same way, I would get 1.999. So here, as these x values get closer and closer to 1, what are these y values doing? They're getting closer and closer to 2. Here I'm approaching from the left. So y values So in other words, I would say that the limit as x approaches 1 from the left of f of x is equal to 2. The notation I'm going to use for therefore, by the way, is these 3 dots arranged in a triangle like that. That's a shorthand for the word therefore. Hence, thus. Does everybody understand what we did there? Are there any better phrase? Any questions about what we did there with plugging in those numbers? So I plugged in 0.9, 0.99, and 0.999 for x, because those are numbers that get closer and closer and closer to 1 from the left. And I was asked to investigate what happens as we get close to 1 from the left. Is that clear? If we want to come in from the right, I can do the same thing. I might look at f of 1.1, f of 1.01, f of 1.001. So I'm looking at inputs, x values, that get closer and closer to 1 now, but from the right. 1.1 is bigger than 1. 1.01 is bigger than 1, and it's even closer to 1 than 1.1. 1.001, well, that's getting really close to 1. So if these y values that I get out are getting closer and closer and closer to 2, like this is, say the limit as x approaches 1 from the right is equal to 2 as well. So let's see that. Let's go ahead and do those computations. And then I'll show you a quick way to deduce this algebraically. F of 1.1, well, that's what I get when I plug in 1.1 for x. So that means I need to take 1.1, square it, subtract 1 from that, and then divide that by 1.1 minus 1. And I get 2.1. If I play the same game with 1.01, that is, I take 1.01, square it, subtract 1, and then I divide that by 1.01 minus 1. That's f of 1.01, that's 2.01. And if I were to do the same thing here, I would get 2.001. So from the left, these y values are getting closer and closer to 2. From the right, these y values are getting closer and closer to 2, right? 2.1, that's a little bigger than 2. That's 1/10 larger than 2. 2.01, well, that's closer to 2 than this. That's 1/100th larger than 2. And this is just 1/1000th larger than 2. So I would say as x gets closer and closer to 1 from the right, the y values are getting closer and closer to 2. Therefore, the limit as x approaches 1 from the right of f of x is also equal to 2. And altogether, this shows, or this suggests, that the limit as x approaches 1 of f of x exists and is equal to 2. Okay. That's the idea. So as my x's get closer and closer to 1, whether I come in from the left or whether I come in from the right, the y values, the corresponding outputs, are getting closer and closer to 2. Since the left limit and the right limit are the same, they're both equal to 2, I say that the overall limit exists and is equal to 2. But f of 1 here, remember, isn't defined. F of 1 is definitely not 2. F of 1 does not exist. So what does the graph of this function look like? So first, questions about this numerical investigation before I move away from that. Any questions about what we did here and why, or what any of it means? Okay. So continuing with that same, still working within this same example, I'll write the function down again. We just showed that we think limit x to 1 of f of x is equal to 2. Can we prove it? So mathematics is all about proof, right? We're not interested in, well, we are interested in conjectures. Conjectures are good, but whenever we have a guess that we think is true, like something that we get from a table or some sort of numerical analysis, we would like to come up with a proof. And thankfully, yeah, there is another method. So what we're going to do now is just a little bit of algebra. I don't want to have to make a big table like that every time. It's a pain in the ass. And frankly, I hate this calculator. It's the worst thing on the planet. So how do I banish that stuff from my existence? I need to be sneaky, algebraically. F of x, which is x squared minus 1 over x minus 1, can actually be simplified quite a bit. X squared minus 1 factors, that's x minus 1 times x plus 1. So this whole thing is x minus 1 times x plus 1 over x minus 1. And that denominator has a factor of x minus 1 that I can cancel with the top. So this is the same as x plus 1 over 1, which is just x plus 1. But this is only true, you can only do this cancellation. This step right here is only true if x is not equal to 1. So especially people who took trig with me, you remember me being pretty tough about our identities and equation solving, saying, you know, if you cancel something on both sides, you're losing information, right? That those things are only true if you stay away from whatever makes the canceled factor equal to 0. Well, here this canceled factor of x minus 1 is equal to 0 if x is equal to 1. So I can only say that this thing is equal to this thing if you stay away from x equals 1. This thing is undefined when x is equal to 1. This thing is defined when x is equal to 1. So these guys are equal everywhere but here. That's the big idea. So if I wanted to draw a graph of f of x, that's not hard. I know everywhere except at x equals 1, f of x is equal to x plus 1. Well, that's easy. That's a line, it's slope 1, y-intercept equal to 1. It looks like this. But over here, when x is actually equal to 1, we have a hole. So this is the graph of that function. Doesn't look like its graph would be a straight line because it's got that x squared minus 1 upstairs and an x minus 1 downstairs. It looks like it would look like all the other rational function graphs you saw, that it might have some asymptotes, it might have some weird shit, but it doesn't, because there's this factor that cancels top to bottom. Everywhere away from x equals 1, this function behaves like this line. The only difference between this function and this line is that this function is undefined when x is equal to 1, which means there's a hole there. And so instead of doing that numerical investigation, we could have said, since f of x is equal to x plus 1 for all x different from 1, we know that lim x to 1 of f of x is equal to lim x to 1 of x plus 1, and that's just going to be 1 plus 1, which is 2. And what we're getting close to here are what are called some limit laws. So I'm going to show you the limit laws, but not today. I don't want to jump too quickly. The first bits of your homework, and what I would like you to start working on following today's lecture, is all about calculating limits from graphs. There are some weird things that can happen, and you're going to find in some of those problems there's some challenging shit there. Like what happens when you've got a piecewise function that disagrees at either end, or what happens if you have a function that starts oscillating really rapidly as x gets closer and closer to some value. What happens if one side starts oscillating and the other side blows up to infinity? All of those sort of questions you're going to play around with in the homework, and I want you to struggle with them a little bit. I want you to look just at the graph problems and really work on those for a while. The second little bit of the homework is going to be doing stuff like this, where I give you a function that's maybe undefined, but I want you to take the limit at that point where it's undefined. And in order to do that, you're going to have to factor and cancel something. And then that will lead us nicely into the discussion of the limit laws. So the first limit law, and if you want to think about this, you can just go ahead, is that the easiest way to take a limit is just plug the damn number in. Right? If I ask you to take the limit of a function as x gets closer and closer to 5, first thing you should always try to do, plug in x equals 5. If it works, it works. That's awesome. And if your function is continuous, it will always work. But most of the functions we're going to play around with are not going to be continuous. They will be discontinuous at that point of interest. So then the second kind of approach that is nice and direct, if you can't get there just by plugging in right away, try to do some algebra and then plug in. And that's going to be the main method that we have later in chapter 2 for calculating limits. You're going to do some algebra, cancel a factor, and then you'll be able to plug in the desired limit value. There will still be some problems where we can't do that. And for those problems, we're going to need specific approaches. Sometimes it'll be geometric, sometimes it'll come from a picture, sometimes it'll be something else. But for the most part, we're going to work most, just like this, either from the graph or we'll do some algebra, cancel a factor, and plug in. The first thing you should always try to do when you're asked to calculate a limit, just plug the number in. If you can't do that, then you need to start strategizing. And my recommendation to you at this point in the first few days of Calc 1 would be to draw a graph. All right, would be to draw a graph. For example, and this is the last one I'm going to do today. We're doing okay on time?
I do have an observation type question.
Sure, yeah.
So I'm assuming we're going to need to find the point of the whole. So would we just say that the point is for nearly everyone that's not continuous, whatever the limit equals as it approaches, and the whatever the denominator is set to 0. So that one is 1, 2, because 1 minus 1 is 0. And the limit reaches 2.
Entirely sure I follow the question. Could you just rephrase that? There was a little bit of other stuff going on in the background. I couldn't quite hear you.
That's okay. We need to find the point of the whole, I'm assuming. We need to...
That's the idea. Yeah, we're looking for the y value. If your function is discontinuous at the place you're trying to take the limit, then what you're effectively looking for is the y value of the whole. Yep.
And is that always going to be what the limit is when it approaches 1, and then whatever the denominator is equal to 0?
If the thing that you're playing around with is a function that has a whole in it, then yes. But that's not always going to be the case. So most of the time, for these interesting or challenging problems, that will be true. But sometimes you don't have a whole. Sometimes you have a vertical asymptote, and then we would say the limit is infinity or doesn't exist. So we'll have to look at the other things that can happen carefully. But for most of the examples we're going to be talking about, yes, you'll be looking for the y value of the whole. And if the function is a rational function, then you'll be able to identify the x value by seeing where the bottom is 0. But the trick for us is usually not going to require that, because we'll be asking, hey, find the limit for this function as x goes to 3 or 5 or 10. So you'll already be told what x value you're looking nearby. And then to find the y value, it'll usually be a factor and cancel sort of trick, something like that. But don't stress too much right now on that, because all the problems that I want you to be working on, for now at least, you'll have a picture. You'll be working just straight from the graph, and I want you to think about it just in terms of the picture for now.
Okay, cool. Thank you.
Of course, of course. All right, so the last little problem I want to look at with you guys today says, let's see if you can find the limit as x goes to 0 of this function, sine x over x. And that's a weird function. That's not a function you would study in a pre-calculus class, because it's got some trig in it. And it's not really a function you would study in a trig class, because it's got some non-trig stuff in it. So one way to get started with this would be to use a graphing utility, something like Desmos. So that's what I'm going to do. I'm going to pull up my browser and go to desmos.com. And I'm just going to type in f of x equals sine x over x. This is a really interesting function. This function has a name. It's really important to mathematicians who study the sort of stuff I study, number theorists. It's called the sink function, like kitchen sink. You see that it does wobble back and forth. Another place I could look at a graph of this that's better scaled is Wolfram alpha. So while I'm showing you these things, we might as well show you all of them. Type that guy in, and he'll give me a nice picture of the graph. Desmos always scales the horizontal and vertical axes the same. Wolfram will scale things to give you the best possible picture. So here is the picture of that function near 0, right? This is the graph of sine x over x. His graph, come back to the dot cam now, we've got a pretty good idea. His graph looks like this. Except there's a hole here. And so like Angelica was asking, what is it we're trying to do? Well, when I say I want to find that limit, that means really what I'm looking for is the y value of that hole. You can think of your little dude trying to meet up with his girlfriend. They're both going to walk closer and closer to x equals 0, but they're going to do that along the graph. And if you look at these graphs, you'll see that the y value up there we might not actually get to 1, but we get very, very close, right? So if I track this point, as I move in closer and closer and closer to 0, what are those y values getting closer and closer to? Well, that's 0.9, 0.998, 0.9983, 0.999, getting closer and closer and closer to 1. However, when we're actually there at 0, the function is undefined. Right, there's the hole there. Similarly, if I was to walk in from the left, getting closer and closer and closer to 0, those y values, if you track that point, those y values are getting closer and closer and closer and closer to 1. But then when I actually get to 0 there, he's undefined. So I would say that this limit, so from graphical investigation, or just from the graph, we see that the limit as x goes to 0 from the left of sine x over x is equal to 1, and that's also equal to the limit as x goes to 0 from the right of sine x over x. Therefore, the overall limit, the limit that doesn't have a minus or a plus for this thing, sine x over x, is equal to 1. This is going to be a really important limit for us a little bit later when we start looking at derivatives, and specifically derivatives of trig functions. This is going to be a special limit that we're going to have to remember. Right now, we can get it from the graph, and that's nice. We're also going to come up with a geometric argument to prove this limit. And then I think at one point down the road, we'll also have a third way to get this called L'Hopital's rule. But that's way off in the future. So what I'm asking you guys to do, what I would like you to be doing today, tomorrow, is get into that WebAssign homework and solve the problems that ask you to find limits of functions using the graph. I can show you one or two of them briefly here. And then on Friday, I will start playing around with some of these algebraic techniques. So just briefly, has anybody had a problem getting into WebAssign? Anybody not been able to get in? Remember that you don't access code. All you need is the class key. When you get to the page that asks you for your access code, you can scroll down and say, I want to use the temporary access. Yeah, there was a question. Somebody was saying something.
Just earlier, for some odd reason, it threw me out of Zoom, and I kept trying to get on, but I don't know if that, like I'm kind of afraid it's gonna happen the next time, like on Friday, because I just had a really hard time getting on Zoom. It's not WebAssign related. It's just, I don't know if that's something, we have to look at. Sorry about that.
Writing might be worth calling or writing to Zoom's tech support. What exactly happened?
I forget exactly what it said, but it kept saying that it was not supported or something like that. And so it had me download this thing, and I downloaded it, and then just, it was really weird. Then I had to download another one, and then I had to get out of it because it wanted some code ID. And so then I tried again clicking from yours. Eventually, like after the fourth try, I finally get back on again. It was weird because I was already on it, and it just pulled me out. So I don't know what.
The problem that she's describing, where you're getting kicked out of Zoom, Zoom crashes or does something weird when you try to join the meeting? Anybody else experience that?
What OS do you have?
Yeah, that's a good question. Lynn, what operating system are you using? Is it iOS? Are you on a Mac or a Windows or a Linux computer? What you doing?
Me? I don't know. I'm really not very knowledgeable on computers. I think I have.
I think the thing to do, in order to keep class time class focused is write me a Canvas message, and then also go ahead and open a support ticket with Zoom's technical support, and we'll try to get that figured out. I do record the lectures, and you can always rewatch them on YouTube, but it is important that you're here and that you're able to participate in our conversations. My Zoom client crashes not infrequently also, especially when I first join a meeting. It often stutters and then sometimes crashes altogether. It can be super frustrating. I did just get an update for Zoom. So they just pushed a new version of Zoom, and you might want to try downloading the latest version. That might resolve the issue. I'm not sure, but either way, let's go ahead.
That's what it wanted me to do.
Okay. Yeah, it could be.
And it did it.
So it won't happen anymore if you went ahead and did that. But let's go ahead and talk to technical support people there, and then CC me on that email. Antoine, I see your message there. Yes, I did get your emails and I replied to them. You should see a reply in the box and webcam. Last thing I want to do here is take just a brief look at one or two of these problems in WebAssign. So you see this first one is very much like the examples you've been doing. They give you the graph of a function. Go ahead and mute that mic.
Mr. P?
Yeah.
You're kind of cutting up. I can barely hear you.
Yeah, I think someone has their microphone unmuted and we've got a lot of noise coming in. Mute all. Okay, I got it. Can you guys still hear me?
Yes.
Okay, good. All right, so one or two quick looks at these WebAssign problems. You see here they've given you a graph of a function, and then they ask you for a shitload of limits, like what's the limit as x approaches 2 from the left of f of x. So I would look along this graph. I would imagine I'm a little guy walking closer and closer to the point where x is equal to 2. And I see that those y values, as I approach from the left, if you watch my mouse cursor there, my y values are getting closer and closer to this, which is halfway between 2 and 4. That's got to be 3. If I approach 2 from the right, coming down here to part B, that means I'm going to walk along this graph until I get closer and closer to the point whose x value is 2. But I'm walking from the right now. So instead of going up to 3, I'm coming down here, closer and closer to this hole whose y value is 1. And then they'll ask us, well, what's the overall limit at 2? And in this case, we would say that doesn't exist because the left limit is 3 and the right limit is 1. Since the left and right limits aren't equal, that means the overall limit does not exist. They'll have you play that game for a few other things. There's lots of problems like this, and some of them are a bit tricky, like this guy. And then they ask you to find a limit, or this guy. And they ask you to find a limit. So you're going to want to start divorcing in your head the idea of the value of the function at that point, like here, f of 4 is equal to 4. But the limit as x approaches 4 from the left is 3. So the point on the graph is not the same as the value of the limit. The value of the limit comes from what happens nearby. So it's always imagine walking closer and closer. Go ahead and dig into the graphing problems, right? The first 5 or 6 problems here are all built around graphs. And then if you want to get started on some of these guys, maybe like, where was that one? Number 10, some of these other ones that are more graphically based, or number 11, you can go ahead. But know that we still need to talk about some other stuff before you're ready for the remaining problems. So these later problems are going to be about limit laws and algebra rules for calculating limits, things like that. So those are coming from section 2.3. Today we just talked about section 2.2. So go ahead and make sure you knock out those first 5 problems before we meet on Friday. And then on Friday, I'll talk with you about how to solve the remaining ones. You're more than welcome to jump in and work on some of those other problems. In fact, I suggest it. But what I need from you is to make sure you at least solve those first 5. So spend time working on them. If you get stuck on any of them, don't be shy. Send me a Canvas message or an email, something like that. I'll be happy to talk with you about those problems. There's two other things we need to do briefly here before we get out, and that's establish some office hours and also take roll. So the easiest way to take roll is going to be for everybody to just go ahead and type the word here in chat. So if you could open up the chat dialog and just type the word here, and then I can go to our chat log at the end and take roll that way. So take a second and do that. Open up the chat and just type the word here. And then once everybody has done that, we're going to talk about office hours. Okay.
Oh, you didn't participants.
So what I want to do is I want to select 2 or 3 hours out of the week where I can have an open Zoom meeting where I will just be sitting here with Zoom open, waiting for people to show up to ask questions. Normally when we do in-person classes, I'd have like 10 office hours a week. It's not really practical for me to do that in the online setting. So I'm going to start with 3, but I want to make sure that there are 3 which work for you guys. Real quick, Kyrie asked, when will I be uploading the recording? So I've already uploaded the recording from Monday's lecture. You can find that in the Canvas announcement where you found the link to join Monday's lecture. And I'll be uploading the video from today's lecture as soon as I can. It'll be later today, probably early afternoon. So as soon as this finishes, I'll start uploading the video to YouTube. It'll take some time to process. And then as soon as it's done processing, I'll post the link. So if you go to the Canvas announcements, the same place where you find the link to join the stream, you will find the link to the video there as soon as it's available. So coming back to office hours, some times that are convenient for me, I would be happy to do one any of the Monday, Wednesday, Friday stuff as soon as my second class ends. Now my second class, they're kind of weird times, so I want to make sure I'm getting this right. Ends at 12:50. So I could do a 1 to 2 or a 2 to 3 on Monday, Wednesday, and Friday. And then Tuesday, Thursday, I could do pretty much anything. It's all open. So what are some times that would work for you guys? What are some times that you would like to have office hours?
1 to 2 is better for me on Monday, Wednesday, Friday.
So we got 1 vote for this. What else are we thinking? You can.
Monday, Wednesday, and Friday, the time that she said is totally fine with me. In between the times, they conflict with my work, so I'm really more dependent on the days of the classes.
Mm-hmm. Okay, I'm fine with that. Any other thoughts? Is there anybody who wouldn't be able to make one of these? Anybody at all who would not be able to come to a Monday, Wednesday, Friday, 1 to 2 p.m. office hour? You got work or anything like that? Okay, then this is where we're going to start. So the first office hour that I will schedule will be every Monday, Wednesday, and Friday from 1 to 2 p.m. So I will go ahead and post the Zoom link for that office hour. It's always going to be the same link. So the class meeting links, they change, right? Every day I'm going to have a different link, a different meeting, and that's for organizational purposes. But for the office hours, it'll always be the same link, and I'll post that link on Canvas on our homepage, the main page right there. So under office hours where it says TBA, instead of that, there will be just a Zoom link and you can click to join. And anytime Monday, Wednesday, Friday between 1 and 2 p.m., if you click that link, you'll see me sitting here waiting for people to ask questions. So I hope that you do.
Thank you.
I think that is all we had to talk about today. Are there any lingering questions? Anything you guys would like to discuss?
Yes, I would like to ask a question. So like let's just say like you know, I asked questions at your office hours and whatever, and it came to be where I have another question and I can't reach you. I do want to be able to reach the math tutors. I just am having a very hard time between Monday and yesterday and even today this morning. I don't even know where to go to find them.
Oh, very good question. Okay, here. So, if you go to the Learning Commons website, which is here, then right here, you see in this pink box, they say the Learning Commons has added online options for academic success coaching and tutoring. If you come down here, then you can find links to join Zoom meetings for tutoring. So online tutoring support is right here. You go to the tutoring services page. If you're a little bit uncertain how to do it, they've got a little guide there. But if we just go to this, then you can request a tutor, and they will meet you in Zoom, and you can work through problems just like you would normally. So say we wanted to get some help in math and stats. It looks like they want you to go to their Canvas page to kind of talk with them, let them know that you're looking for a tutor, and then they'll match you with a tutor and send you a little message with a Zoom link so you can go and have a Zoom meeting with that tutor. So if you want to ask questions about problems as you're working through homework, just like you would have before where you would go to the library and sit down with a tutor, the only difference is now you go through this website and they have you meet up with a tutor via Zoom.
Alrighty then, thank you.
Yeah, no problem. Any other questions? I did get some questions in chat. So, oh, sorry. I sent that to, I meant to go to Kyrie. So yeah, we'll be, yeah, I'll be uploading the link for today's video in a couple of hours. Anything else? Not a problem. Okay, then that's where I will end today's meeting. Starting on Friday, we are going to work with the limit laws and the algebraic techniques for limits. Make sure you solve those first 5 or 6 WebAssign homework problems. If you do run into any questions, feel free to message me on Canvas or meet up with one of the tutors via Zoom. And then if you have time, go ahead and poke at a few of those other problems, see if you can get a feel for them, but don't stress if you don't get them right away, because we will be talking about how to solve them on Friday. Alrighty. And if you want to talk with me, of course, I will have an office hour this afternoon from 1 to 2. Okay, I will see you guys later.
Thank you so much.
Of course, yeah, have a good day.